This is the Muscle Memory Senior Project for 2021. We are Team 11. The team members in this team are Philip Kaznowski, Catherine Wiesman, Emily Lowry, Caleb Verbrugge, Deidre Bortman, and Mason Convertini. Our project sponsor is the GVSU Biomedical Engineering Committee, and our project advisors are Dr. Blake Ashby as our faculty advisor, and Dr. Samita Rhodes as our sponsor contact, since this is a Grand Valley sponsored project.
The BME committee requested a device that they can use as a demonstrative tool for their K-12 outreach events. Something that would catch young students' attention, introduce them to biomedical engineering and its real-world applications, and spark wonder in them. They wanted something that would turn collected electromyography data, also known as EMG data, from muscles into actuated motion wirelessly. No wires restricting a participant to any computer or to the device. A robotic humanoid arm was decided upon for the device. In addition, the project should be forward-thinking with an open-source software such that future Grand Valley students and faculty could improve upon it or add more functionality to the device. Such a device could also be used for teaching tools in engineering classes. The device we designed and built has three main assemblies: a harness intended to be worn by a participant, the robotic limb, and a computer module. The harness collects EMG readings from a participant and transmits them through radio signals to the limb and computer module. The limb then moves at the shoulder and elbow using the sensor data. The computer module displays a plot of the EMG data on a computer screen or a projector in a classroom.
The wireless EMG harness that we designed is comprised of a few primary components: an MSP432 microcontroller, a battery pack to power that microcontroller, and an NRF module to transmit the EMG data wirelessly to the base. The sensors themselves have an integrated LED, so as the participant flexes, as shown, the brightness of the LED will change according to how strong the participant is flexing their muscle.
This is a video of us testing the EMG sensors early on in the project. The sensor was placed on a bicep, and the data was displayed on the laptop screen. As you can see, the reading starts out flat when the muscle is not being flexed and jumps up after activating the muscle. The data is very jumpy, and we need to limit the rate that the data was being read, process the data, and set thresholds in order to use it to control the arm.
After the EMG readings have been transmitted to the base, this arm, with 3D printed shells to make it look more like a human arm, will move according to the strength of the EMG signals obtained from the harness. Two of the sensors from the harness will work together to control servo 1, one controlling clockwise, the other controlling counterclockwise motion. The other two servos each control servos 2 and 3 individually. Each sensor from the harness is also individually responsible for controlling one of these 4 LEDs. Where the harder the participant flexes, the more LEDs on each ring turns on. The base of this assembly contains a lot of power delivery components that deliver the power to the rest of the components of the assembly in the desired format. There are linear regulators that step down the voltage and smoothen it so that the LEDs don't flicker. There's also a switching regulator whose purpose is to provide sufficient current to the servos as the power draw requirements of the servos change rapidly. The primary microcontroller that we are using for this application is an Arduino Mega. This was selected because of its additional storage and processing power compared to the Arduino Uno. We were able to use a standard off-the-shelf laptop power supply for this system. We were able to integrate the female end of this power supply into a 3D printed housing that also supports the electrical tray. There is an emergency stop that immediately cuts power to the servos when pressed, in case something were to happen, to ensure safety of everyone involved. There are 2 clamps that hold this entire assembly onto a table to ensure that the assembly does not move during operation or does not tip or wobble unnecessarily. This is a demonstration of our device moving through a pre-programmed set of positions. As you can hear from that last clip, this device, although it does make some noise, isn't sufficiently loud to require any sort of sound deadening or any hearing protection during use.
At the time that this video was created, there are 2 weeks left until the completion of the project, and there are still a few things our team is working on. Since this device will be taken to schools, it needs to be transportable, and we are working on a foam-lined suitcase for this purpose. We need to finalize a cover for the electrical components on the limb to make sure that the limb fits snug into the suitcase. This cover will help limit risk of anyone accidentally touching something they shouldn't and wires being moved during transportation. We are debugging the LED code to get all 4 of them to light up in a circle related to the strength of the muscle contraction. We may need to add a cover with foam to dampen the noise coming from the shoulder. The computer module will be an Arduino Nano microcontroller that will receive data from the harness and plot the EMG data on screen to the computer that is connected to. A plot similar to the EMG sensor test video shown earlier will be shown, along with error messages to inform the user of any issues. The computer module is almost done, yet we are working on error codes. And most importantly, we are working on getting all 4 EMG sensors data integrated into the limb code to make the arm move the way we planned. Currently, 3 of the 4 data sets are integrated.
All right, onto performance evaluation. Our design will theoretically meet all of the set specifications if we keep on track. Verification testing on our completed device will still be needed to ensure that all specifications are met, but we do not expect to encounter issues in this process. The limb is capable of moving much faster than needed, with no signs of mechanical overloading or running low on supplied power during maximum loading. This shows that our torque specifications and power requirement calculations were sufficient for our design. The motion as it stands when being fully operated from EMG readings is choppy, with residual vibrations lasting for a few seconds after a hard acceleration or deceleration. We will be attempting to address this in the next couple of weeks using software as much as possible.
Future works. Possibilities for future work include adding mechanical damping to the motion of the limb to reduce residual vibrations that cannot be accounted for in software. Another opportunity for future change is adding attachments to the end of the limb, such as an actuatable claw or hand to move objects around or add more human replicating motions to the demo mode, such as a wave or a fist bump. Adding an aesthetic cover for the whole limb assembly to hide more of the wiring and internal components would likely make the product look even more finished and professional. Something to reduce some of the servo noise would also be beneficial in creating a more finished feel to the product. A projected display for the current position of the limb and a less technical display of the current EMG readings would make the product easier to understand for non-technical audiences and would possibly have more of an impact on the viewer. A computer-based control system would also be beneficial as a manual control mode to have more precise control of the limb.
We believe that this device will be a very useful outreach tool for the BME committee, as we either have already met or will meet all of the required specifications. This device can also be used to show off a lot of the capabilities that we have at Grand Valley, such as the 3D printing for the shells and some of the structural components, as well as the machine shop for all of the custom components within this assembly.